And that is what, if you want to study, let's say, large-scale integration of solar or wind power, then you have to, I think the grid could be an issue here. And then you have to do the production cost simulation. That is a very simple version I did for earlier. And then, of course, you have a lot of iteration. It may happen that you design a system and then you simulate and you find out this doesn't work. You get too high P, or you don't have capacity enough, or something like this. Then, of course, you have to go back and change the scenarios. So that's why you see all the iterations here. You start with some kind of specific assumptions, and then you have a scenario of your system, and then you find out that, no, this doesn't work. We have stability problems, or we have kind of load flow. We don't have capacities enough. We have to have more grid. You have to go up and go around like this. So this is just a general, I mean, this is, of course, just, you can call it logics in some way. What you will get is also this with capacity value. That is something I will talk a little about, the so-called adequacy. In my, what I wrote yesterday, it was extremely simple in the tutorial because it was only deterministic. I said that we have a demand like this, we have a capacity like this, then of course it will not work. So we will of course get an outage. In reality, this is some kind of risk, because if you have coal power plants, the availability, you have a certain forced outage rates in the power plants and so on. So there is always, you can never say that there will be a certain outage. There is a risk, and the risk is certain percent, which means, and then the question, so, which is a probabilistic approach. While most of the things here, I mean, load flow, there are probabilistic load flows, but I mean, dynamics is always done for a specific, very specific situation. If the wind is like this, if these coal plants are there, if we have a transmission like this, if the load is like this, and we get a disturbance, then of course we get these kind of things. In reality, you have a huge amount of possible situations. I mean, just take India. How many combinations do you have of outages in different kind of power plants, and the load is changing like this, there, and so on. So that is one of, let's say, the challenge, especially when you come into both dynamics, but load flow is so fast, so that's not a problem. You can run a huge amount of load flows, but when you come into dynamics, the question is, which cases should I really test? I cannot test all the cases because it's just too much work, also in the computer. But on the other hand, when you talk about loss of load probability, remember the last, that OLP, the probability. Just to say something, if you include something called probability, you must study a huge amount of situations, or you can have analytical solutions working with duration curves and this kind of thing. So there are probabilistics. You have to have studied many different possibilities that could have. You can have outages in the power system, you can have outages in power plants, it could be low load and at the same time high solar power, or low solar and high load. So then it starts to really be challenging this with capacity. So that's one of the issues we are working with. I will say a little more about that later. So this is just, and then the challenge is also when you come in. I mean, in reality, this is extremely complicated. I mean, on the other hand, there's a huge amount of PhD students all over the world, but that doesn't mean that we don't need PhD students in 10 years. Of course we will need. I mean, here I'm in reality talking about how to design a power system, including everything. I mean, everyone that is working in a PhD thesis is sometimes working somewhere here. Because this is explaining nearly everything in the power system, which of course is a very big challenge. You cannot, now we make a study of India and then it should be finished in 3 months and we should consider everything. It's of course impossible to do that. So this is, you can call it a target, that this is of course the best thing you should do. But on the other hand, it's also important that, let's say we skip this dynamics, then you must know that this may be a problem because we have not studied the dynamics, and this may be a problem because we have not considered this. It's important when you do things to say, what have you considered and what have you not considered? For example, this with distribution. We, for example, say that, okay, we have assumed that the distribution system works and we have a perfect transmission system within each state of India, so then we just have each state as one point, and then we have the transmission between the states. Of course you can do that, but then you say that, okay, this will work, and then you can take the next step. Okay, will it work in reality? Then I have to study each state by themselves and just dimension the distribution system or something like this. So I think this is, you can call it the goal, this is the whole, everything here, but then in reality, of course, you can never do all this. It's too much. So this, I will go to something else. Capacity value, I will come back to that. This is just one thing. They have tested in Ireland. The question was, how many years of data do you need? Because different years, at least in Ireland. Now Ireland is a very much smaller area than India, for example. But I'm sure that in India it can be some years it's very hot in that area sometimes, and sometimes another year very hot in that area. So if you really want to get, let's say, how much can the weather vary, what they have found out in Ireland was that they at least needed 7-8 years in order to get some kind of robust results in this. If that is true for India or not, I don't know, because I don't know how stable the weather is here between different years. Of course, it's not stable. I don't take all the... There is a paper on this that was presented in October now. Just this is a recent paper, which is... Okay, so these are all the countries that are involved in this cooperation. So that's why I talk a lot when I say something about Ireland, United States, what is happening in Italy and so on, and Portugal. I said this about 104%. The issue is that if I know how much right now, I just send an email to the Portuguese representative, Ana Estanqueiro, or if I want to know something about Norway, or something, and that this is extremely good network, I can say, in order to get. And here the whole idea is design and operation of power system with large amounts of wind power. But nowadays we also have solar power, which is coming in. That is because that has happened in the last years. Then I have another which I will go through, and that is, I coordinated this paper, and that was also presented in October here in Berlin. And that is a comparison of integration studies of 30-40% energy share from variable renewable sources. I earlier said, assume that you have 20% solar power in India. Yes, that is of course an issue, but the ambitions, there have been many studies done with up to 30-40%. But not for India. I have not seen anything. But on the other hand, it may depend on that India is not here. So there may be, I don't know, that may be a study that have studied, let's say, exactly what I'm talking about now, that have done a very good study of large amount of solar or wind power in India. I don't know. But anyhow, what I studied here is that there have been several studies. And the interesting thing is that, because this is the whole world. I mean, the end aim here, what is the aim of my lectures, is integration of high penetration of solar and wind power in power systems. The question has always been, what is high? Since you're an engineer, what is high? What do you mean with penetration? Solar, I think, is rather easy. But then I think, so integration of high penetration, this word with high, and what I have identified during the last, I can say 5-6 years, I think, is that this 30-40%, that is possible without any extreme things. And when I say extreme things, and that is, in Germany, for example, they are discussing 80%. If you have 80% from solar and wind power, this means that you sometimes will get double as much production as you have demand. And I think that if you have solar power and wind power in India, and that should cover, let's say, 50, 60, 70% of your yearly demand, I think that then you probably need some kind of more you can call it new technologies. Like what you can have is this, of course, that you do electrolysis of water and you get hydrogen, and the hydrogen is then stored or reformed to methane or something like that. I think I don't know how much you worked with that, but you have electricity here, and from electricity you can have the H2O, which you divide O, so it should be 2 here. You get O2, and then you get 2. So you get that hydrogen, and that you can combine with coal if you want, and then you get CH4. Then you should multiply with some things. You have learned your chemistry sometimes, and this is the same as the natural gas. So this is, you can do this kind of thing, or you can directly in fuel cells, and then you get electricity. So this is a way to really, I mean, this is technically possible. That, I mean, no one say that this doesn't work. The problem is that this is expensive. This is expensive. And here you lose efficiency. When you go from this one to this one, you also lose efficiency. So it may happen that in this cycle you use much more efficiency compared to an ordinary battery, for example. But on the other hand, here you can store a lot. So I mean, here you can store, there's no, let's say, physical limit in reality how much you store. On the other hand, this is more complicated. I mean, this is a very small atom. So I mean, it's much more difficult compared to natural gas. You have storage for. That's, you can have ships with so on. You have ships with liquefied natural gas, for example. Then you cool it down and transport it, for example, from Saudi Arabia to Japan. They do it. So that is common. So this is a conventional product. But to store this one, it's possible, but I think this is easy. But here you lose energy in all these kind of different things. But of course, this is so. But on the other hand, my conclusion is that yes, very interesting, but 30–40%, this is not needed. That is the conclusion we have had so far, and this is after looking on rather many studies. Then that is, you can call it the background of this, because everyone is talking about we need storage, and our conclusion is that yes, storage is good, but you don't so-called need it if you have only 30–40% of variable renewables in the power system. And we have studied several systems here. So this is a cooperation of me and concerning Germany, and then we have 2 persons from EDF, which is the Vera Silva and Miguel. They are from EDF, Électricité de France. That is the biggest producer, state-owned in France. And we have Michael Milligan and Barbara here from NREL in the United States. And then we have one guy from Ireland, and then we have Juha Kiviluoma. He's from Finland, but they have made a study for Iberia, I think for Spain and Portugal. And then we have Antje Orts. She's she's working with very much with the whole European transmission grid, but she's German but employed in Denmark. And we have wrote this paper together. So I will go through this, but then I think I will not take all the details. There is in this, both in this paper and in for each country, I will take perhaps one country. There have been a huge amount of studies in these countries, all these in Sweden, Germany, Iberia, Ireland, Europe, 2 studies for Europe, and 1 from US in Minnesota. And we have studied different shares of wind, of variable renewable, solar plus wind power. And then the question then, of course, how much, that is one of the, that's why I have this kind of thing. Because let's say you have an area like this, okay? And here power, and then you have solar power. And this is varying. And then the question is that has to be balanced. The question is, do you balance it within this area, or do you balance it here? Of course, if you have it in this area and you have a huge amount of transmission here, then I mean this area is not so interesting, because you can maybe do everything in that area. That is, this can, for example, Denmark is this type. You have Denmark here, but everything is balanced in reality in Norway and Sweden. So how much interconnection you have. And if we take, for example, India as an example, a state has, of course, interconnections to the neighboring state, but India doesn't have any interconnections. So that because of that, we have to consider these kind of things. So if Sweden is the same study that I showed you earlier, I assumed that isolated Sweden. While in the German study, they have assumed that they have interconnections, so some of the balancing can be done in the neighboring countries, which of course has an impact on the result. It can have a big impact on the result. And in the Iberia Peninsula, they didn't have any connections, and then you have big European studies. And the European studies, of course, Europe is as big as in that point of view, so Europe doesn't have any interconnections to other parts. Europe has. We have interconnections to Africa and to Russia, for example. When I say Europe, Russia, I mean part of Russia, but this is more EU. And US, Minnesota, they have in reality also rather good interconnections to their neighbors. This, and I think this is of course important, but this is as important, because I mean if you get help from your neighbors, I mean you want to balance it in your area. So then of course this is what is percent, because when you say percent of what? You're extremely good connected. The percent should not be in this area, the percent should be in the whole area here. So in this report, I have in this paper we have studied all of countries. The problem is that these studies are made rather differently. And as I showed you earlier, when you make this kind of integration studies, you can have a lot of different combinations. Do you have CO2 as an input that you should have a price, or do you have as an output? Do you have a limit on? Do you have a requirement on wind power, or is it an output? So, of course, the whole idea of the report is very different. So this is, of course, that the aim will, of course, then you have different input in one report, maybe an output in another report. I can say, yes, one thing about these studies. I think this report, or one report here, one Europe report, is made by the system operators in Europe. The question for them was, okay, if we have a huge amount of solar and wind power, do we need to strengthen the transmission network? That was their problem. The other report is made by a producer. They think that, okay, in the future, we will have a certain transmission system. Assume that we have a huge amount of solar and wind power. What happens with the production? So it's the same type of study, but they have completely different aims. One is about, should we expand the transmission system? And then, of course, the output is, how much transmission do we need? While in the other report is more, okay, how much spillage will we have as a result, and so on. So they are different aims here. While one aim is transmission expansion, because it's made by the companies that owns the transmission, while the other ones have the producer perspective. So, and that is, of course, different results here. And that is, of course, that when you see this kind of report, you must first check who has done it, why. And then, of course, in this case, one company said that one of the results is that we need so much transmission is the output. But in the other one, the transmission was more the input. And then, of course, then the results of one, then, of course, I read this one, they didn't say anything about new transmission. No, because that was the input. So this with input and output, whatever you read for kind of technical report, try to identify what is the input and what is the output. That's also what I convince my PhD students, and it's not all, they come with their model, and then I wonder, okay, you have a model, what is the input, what is the output? And that must, of course, be clear. And then, of course, why did you do it? For example, I've seen studies in Sweden where they said that the aim of the report was, what is the consequence of having 30 terawatt hours of wind power in Sweden? And then the output was, it is possible to integrate 30 terawatt hours of wind power. And then people said that, I have read the report here, that said that it's possible to integrate 30 terawatt hour of wind power in Sweden. And then I said that that was not the output from the report, that was the input to the report. You cannot say that, you cannot claim, you cannot, and it's the same thing, sometimes you see that you have a report in Europe that says that we will increase wind power with 20% and we should decrease the CO2. And that is the input. Then of course you cannot say that. We have made a big study. It's possible to decrease the CO2. Of course, that was the input to the report. So, I mean, and I think it's a bit too often I see these kind of things that people try to draw conclusions. You can never, if you have a model, you can never draw conclusions from the input. You can only draw conclusions because the conclusion is what you get is the relation between this one and this one. So it's extremely input whatever, and I can generally say, when I read these reports, it's very often, and when I see a paper, and I mean, to really identify, okay, you have a model, what is the input, what is the output? And then of course, what is important is, of course, then the sensitivity. If you change this, how much will this change? But I mean, whatever the model you have, what is that? What is that? Draw conclusion about that, not about that. So, this is a report about Sweden, but I don't think I have time to go through. This will take a lot of time because I have it for all the different countries here. This is the results. I will only take up, we have summarized some general conclusions here. Additional storage for system-level demand generation balancing has not been found necessary in any of these studies. And that is, as I say, that's everyone is talking about storage is needed. But up to this 30-40%, we have not found in any of these studies that it's needed. Because the problem is that people working with batteries, they often say that, yes, when we have more and solar and wind power, of course we will need batteries. Yes, I know, but remember there is other kind of storage in the power system. You have coal power that can go up and down. They have a big storage which is called when they want coal, call it. They have a lot of storage already. Or if you have a hydro reservoir, it's more the same. You have that is filled. You don't have any limits in the storage, but still it's some kind of storage you have there. So, and when we talk about additional storage, we talked about this pumped storage, we talked about batteries or this hydrogen or something. I don't think, and that is, let's say, a general conclusion, that up to 30-40%, I really doubt that you can motivate that it's economical. I don't say that it's not possible. I just say that it's expensive. And that is, it was also the same thing, if you remember, in the grid study we talked about earlier. Batteries are expensive compared to reactive control. So, it may happen. On the other hand, there may be rules, as you, for example, have in Germany today, where batteries may be an option. But I mean, remember here that system-level demand generation is only, we are looking on the, let's say, the production side. We are not looking on exactly out in the distribution system, because then if you have a bad distribution system and a huge amount of solar power, it may be efficient to have batteries. And then they have the provision of ancillary services and frequency stability. And that is, of course, that, as I said earlier, that if you have 20-30%, you will have rather much wind and solar power sometimes. You can have close to 100%. Remember the Swedish study I had? Then you got the surplus sometimes. Let's this demand. And then you have the solar power. Solar power is something like this. Of course, this is possible. One way is that you curtail. Then you do like that. Is to say that you are here flexible. If the here you have frequency sensitivities, you have primary control in this one. So this one can go up and down here depending on the frequency. And that is, of course, very good, because if you decrease this one, and you only decrease it, then you still need to have other power plants that are participating in the frequency control. And then, of course, you have to charge, you have to have even more margin just because it should be possible to have, for example, a coal plant that can participate in the frequency control. But if the solar power can do the frequency control, you don't have to keep these extra room just to have just in order to have the coal plant or some other power plant that could participate in the frequency control. So there is, of course, big value in having frequency control and these kind of things in the way when you are curtailing. Don't curtail and just cut it to a certain level. Curtail it and then make it active in the primary control and this. And that was both in this frequency stability, that was studied both in this EDF study. But the important issue is I say that it's not necessary to do it, but it's smart. And I think you have to separate between necessary and smart. It's with batteries. It's not needed, but that doesn't say that it may be smart to do it. It can be smart to have it in your private house, so you don't have to sell so much. You can supply your own power in the night, for example, and this kind of thing. So, but it's not needed, I think. And that is, you have to separate what is needed and then what is really what is possible. There are curtailments when you have 30-40%. So here, for example, I curtail, but at the same time I participate in the frequency control. So you will get curtailment. But then, as what I said here is that it's in the range of single-digit percentages. I mean, let's say that you have solar power and it costs so much like this. And then you curtail 1% or 2%. This means technically that the solar power is 2% more expensive because you only use 98% of it, for example. So you can say that, yes, I lose some, and that makes per kilowatt hour the solar power a bit more expensive. But I mean, it's not a price change of 2% that has an impact on if we get a huge amount of solar power or not. The question is if it can decrease the price with 40% or something. Maximum 1 hour ramp for total wind power is in the range of 8 to 10%. That is what we have studied. So wind power changes, but I mean, I think compared to solar power, I think solar power can in 1 hour change much more. So wind power is in reality changing less if you have it over a larger area compared to solar power, because solar power you go up in the morning and then it goes up and then down in the evening again. There can be extra cost for extra capacity. That is what we needed in Sweden, and that is that we took away some old power plants, the nuclear power that will be dismantled sooner or later. And then you need some kind of our power plants. In our case, what I did, a very simple calculation for Sweden, is that we put in open cycle gas turbines. And but that is, if you see the total cost, they are only supplying 1% of the cost, 1% of the energy in Sweden. So that is not a very big impact on the cost. These are obvious things. The possibility to balance wind and solar power in a large area decrease the challenge as shown. I mean, yes, if you balance wind power and solar power in a very large area. I mean, Ireland, everything has to, it was the question I showed you earlier, that if you have to, this is more complicated, so they can join, because sometimes the wind is going up there or down there. This is, I think, there is a bit of a difference here compared to India, because I think that here it seems like the solar power is the big issue. I think that you will probably have, I mean, wind, it can be different wind there compared to there. It is. I mean, if you go only, let's say, 50 kilometers, the wind is different. It's going up and down in different ways. Solar power, I think, is more equal. If it's sunny here, there is a time shift here, but that is not so much. If you take two neighboring states in India, I think that probably the solar power will be around the same in both areas. So there, these interconnections do not have really as much value as it has in Europe, where you have wind power, because wind power, then if you interconnect, It's windy there or windy there. But probably the solar power, I don't know exactly how the clouds are moving around in India. I have not seen any of this. If there may be, because if there are clouds, so sometimes it's cloudy there, sometimes it's cloudy there, then of course, or the clouds are moving like this, then of course there is a value of interconnections, because sometimes you can import from the solar power like that, and sometimes you can import like this. But if it's the same weather, of course not in whole India, but in the neighboring states, then the transmission value is not as much as if you have wind power. So wind power more creates a need of transmission lines. So more transmission reduces the need of curtailment. But I think that mainly depends on that we are very much discussing wind power in Europe, not so much solar power yet. Okay. Now I will talk about capacity value. This is in reality to manage the loss of load probability. This is very much discussed mainly for wind power, but also for solar power. Let's say you have in a certain power system a certain capacity deficit. You can just make a simple example. We have the demand is something like this. And then let's say we take a pure thermal power system. And then we have a capacity like this. Okay, and it's 100% reliable. Here, we get a deficit. Here, we get a deficit. And here, okay, just to get some kind of feeling, what is the percentage of time that we get a deficit here? Here, here, and here. If we just try to add them up here. Okay, so this is the amount of time with deficit. And this, the whole. This means in this case that the LOLP is equal to, what is it? This is 30% around. Because this is 1/3 of the time. Near one, I think this is, yeah, 30%. Okay. Does that mean, first of all, it's important that 30% demand is curtailed? No. How much demand is curtailed here? This, and this. So you have to really try to understand when we are talking about power system reliability what we are talking about. LOLP, because people say that this is an extreme bad power system. Your reliability is only 70%. Because during 30% of the time, you have an outage. Your reliability is 70%. Of course, seems extremely bad. Does that mean that, okay, so the probability that I will get my electricity is only 70%? No, that's not what I said. I said that during 70% of the time we can supply all the consumers, but during 30% of the time we can only supply 95% or 99% of the consumers. So you really have to understand that when people are talking about reliability, they mean different things here. So and then you have the thing again, also always when you have to be a perfect engineer, if someone say the reliability is X%, and then you have to answer, how do you define that? If you don't know the definition, the figure doesn't say you anything. Because what you see here, and then the question is, how much of the energy is curtailed? I don't know about India. It's said that you have curtailments here, and you have you curtail demand sometimes, and so on. The question is, how much do you really curtail? And I think that here we curtail during 30% of the time. But how much do we curtail of the load? It's during 30% of the time we curtail, let's say, this is, how much is this? This is perhaps only, it's less than 10%. This is 10. Okay, this is 5%. So during 30% of the time, we curtail 5% of the energy. Curtail times 0.05 is equal to 0.015, which is 1.5%. So we curtail 1.5% of the energy. That energy reliability is equal to 9% in this case. And that is, of course, important to remember that when you are talking about a certain thing, you have to, and of course, if someone say that the reliability is 70%, which is correct from the LOLP point of view, but the energy from the energy point of view is 98.5%, which of course is a completely different figure. And when what we are talking about here, that, and then sometimes we talk about power system reliability. Sometimes you talk about the energy and sometimes about the LOP, and it's of course important to know what we are talking about. But here, the definition is very much, I had both in my sheet there earlier, I had both of these. Capacity credit means the possibility of a power plant to increase the reliability. And then I say reliability measured as speed. So the question, and I will come into if there any, and then the question is that is there any capacity credit for wind power? Has been discussed. You cannot rely on it. It's the same with solar power. You cannot rely on it. So you cannot have any capacity credit. You cannot rely on it. And then the question is, can you rely on a coal power plant? No, it can break. And then it starts to be that you cannot rely on any power plant. So you cannot rely on anything, which is of course not correct. You just have to have margins. And a fair way of comparing them, this is with this so-called called capacity credit. What, of course, a power plant, and that has to do with if you have a coal power plant that is running all the year, but then it's you have problems, let's say 1 week or 2 weeks a year, then of course that power plant is much more reliable and have better value than if you have a wind power plant of the same size, but it's going up and down like this depending on the wind. So I will show you, and then you can calculate this in a slightly different way. Wind power, I will illustrate it here with just some drawings. Wind power capacity credit expressed here as equivalent load increase. How much can the consumption increase when the amount of wind power increases and the risk of power deficit is constant, is kept constant? And I say the risk of power deficit. Remember that the risk of power deficit is not the same as what is the risk that I will be curtailed. This is the risk of power deficit. During 30% of the time, there is a power deficit in this system. But how much I curtail, what is the risk that I curtail? I don't know when they curtail, if I'm here or if I'm here. And there is a 95% possibility that I'm among the ones that are not curtailed. So the risk that I am curtailed in a system with 70% reliability is only 1.5%. So we take one specific case here. It's more or less the same type as we have there. We have a specific demand, and the very, very simple case, we have a demand that is changing here. Remember, there are two words here. You have demand, you have load, and you consumers, and you have customers. In Sweden, you know, when you make a load flow or a dynamic simulation, you treat the consumers as a load. As someone told you that you are a load, that's not so positive. So and that is a problem, because sometimes when you have people that have worked a bit too long in the power industry starts to talk about consumers as being a load, that is not so nice. And that, of course, when you have a deregulated market, they are the ones that are paying you. They are your customers. So you should, of course, call them customers. But then you have another issue, and that is the difference between the demand and the load. Because remember here is the capacity of the system. The load can never be higher than the capacity. So this can, of course, not be the load, because the load cannot be higher than the capacity. But on the other hand, this can be the demand. People would like to consume on this level, but they can only consider on this level. So you have to separate between demand and load. And that is the electrical engineering. Don't talk to ones that are paying your business that they are a load, because that's a very negative thing of seeing it. They are your nice customers that are paying your life. They are paying your salary if you work in the industry. You work at the university, they are still paying your life because they are paying the taxes that are paying your salary. Okay, so this is one case. Here we have a deficit in total 40 hours. And then we get wind. Now we put in wind. The wind is the red thing here. So what you see, that wind is sometimes increasing the production, but not always. So what happens when you get wind? You take away some of the problems. What you saw here, that the reliability increased. Here you have deficit during 40 hours, then you have wind, then you got deficit only in 27 hours. You managed to take away some of the problems earlier. What you can say that, okay, but then I can have higher demand. So you can have, so first you have a specific load and a specific a specific demand and a specific capacity in your system, so then you got a deficit of 40 hours. Then you put in wind power, and thanks to wind power you got a better reliability in the system. It decreased from 40 hours to 27 hours. And then thanks to that you can say that, but 40 was okay, so I can accept a higher demand. So no wind power, I install wind power, and thanks to the wind power I can accept an increased load. This means that then I increase the demand until I get the same deficit as earlier. This is the capacity credit. What is interesting, I'm extremely surprised, because today you see a lot of people coming with papers where you say, oh, this is wind power capacity credit. Why I've calculated wind power capacity credit. Sometimes I wonder, sorry, what is new? I made papers in 1986 on wind power capacity credit, and I think I had 5 or 10 references of wind power capacity credit that was made in the 70s with more or less the same method. Australia was very in advance in that time. So This is absolutely in any way anything new. So if I follow my A, B, C, D, E, it's very hard to claim that anything is new here. You really have to find something. Okay, so in this case, the wind power capacity credit is classified as 300 megawatt. Because thanks to this wind power, you could accept that the demand is 300 megawatt higher. But then you see here that the wind power in this case is something like 1500 megawatt or something. So 1500 megawatt of wind power had a capacity credit of 300 megawatt, which is of course very low. It's 20%, which is a very common figure. Wind power capacity credits is free. On the other hand, I think I have not, of course, not made the studies, but I'm saying in India, the capacity credit of solar power is probably rather high, because when you have the solar power, at least in the beginning, problem is that you will not, because the peak will be when it's not sunny anymore. So the capacity credit of solar power in India is probably very high, but then when you increase amount of solar power, then of course the capacity credit of wind power will decrease, because you cannot have 100% solar power. It's the same with wind power. The more wind power you have, the lower the capacity value or capacity credit that is called. So it's this is you can do things like this. This is from the program that you saw. I thought I had. I will wait. No, I forgot. I thought I made something here. I can take one thing I'm working with now, which is one of our latest publications, and that is the following. Let's say you have an area like this. Then what I did here is very relevant. This thing, that's very relevant, because what you see here is the one area. So here you can see calculate the credit, and that you can in reality do with the type of program that I used earlier, that if you increase the wind power with a certain amount of megawatt, how much does the LOLP decrease? The issue, and that is what we are doing now at KTH, is that reality doesn't look like that. The reality looks like this. And you have limited transmission capabilities here everywhere, and you have wind here, you have wind here, you have wind here, you have demand here, and then you have solar power here, and then you have wind here, and you have solar power also. And then the question is, what is the LOLP here? In reality, everyone, what I've seen earlier, you have rules for LOLP, for example, in United States. Should not be surprised if you also in India have some kind of LOLP regulation, that if you are responsible for a state, you must have some kind of requirement on the reliability. Because a problem is, let's say these are the Indian states, for example. The problem is then, of course, if you, let's say you have, I think you have state companies, or do you only have a national, or do you have a responsibility for the power system in each state also? No? Yes? Okay, because then of course an issue is that assume that I don't buy enough power plants, then I can import. And then I say that I only buy, and then I rely on my neighbors. And this is of course a problem, that it's very good to rely on your neighbors, but everyone cannot rely on their neighbors all the time, because someone has to have something. So what you normally have, and that is what you have in the United States, you have something called FERC and NERC, they are National Regulation Committees. They have rules for which LOLP you should have in each state. And this means that if I, for example, close down some units here or my demand increases here, then I have to build more power plants here. The problem is then, of course, that in reality, you are relying on your neighbor. And the question is, how do you consider import when you are calculating this LOLP? This means that you have to consider the probability that it's windy here, not windy here, high load there, sunny there, not sunny there, and so on. This starts to be rather complicated. So because of that, we have a PhD student in exactly multi-area reliability analysis. And he has Egil Thomasen, and he's Icelandic, and he has published 2 journal papers. One came just, and he is going to New Zealand now, in reality, to exactly have so he will have a new conference paper in I think it's ISGT in New Zealand, which is in, I think, in 1 month or something. So he's working with multi-area capacity credit. This means that you first have to calculate the LOLP considering the reliability of these lines, reliability of these lines, reliability of the power plants here, how the demand is changing and so on. This starts to be very complicated. Then you are working with something called Monte Carlo methods. Have anyone worked here with Monte Carlo methods? Okay, you have worked? Because that is a challenge in itself to get efficient Monte Carlo methods. So that is what we have worked with here. And that is that you are, let's say, looking on different states. But then in order, Monte Carlo simulation is that there's a huge amount of possible situations here. It can be windy here, not windy there, and so on. The challenge is to find what are the real problems. When it's very windy everywhere, you have no problems. So then you have something called importance sampling, which means that you're trying to get the important points. This is one of the Monte Carlo methods, because the idea is to really identify, because it's the risk of capacity deficit is normally very small. It's in the range of % or lower. And this means that, of course, when it's very low demand everywhere, and we have very windy or sunny, there's no problem. Why should I make calculations on them? But then you have to identify in some way which situations are the ones, and then I have to study many of the important possibilities, and that is what he have derived specific methods for. And we have also made a study. We are currently trying to apply that for the Nordic system to try to see what is because we are going to build more and more wind power in Sweden, and we are going to take away the old big power plants, in our case the nuclear, because they are becoming very old. And the question is that everyone thinks that we will get more wind power, but then people say that, yeah, but what about the risk of capacity deficit? That is, of course, big. Yes, but we can import. Yeah, but how do you know it's windy on the other side? But you cannot say that it's never windy on the other side. But the cables doesn't work. Okay, we consider that. So we are trying to consider everything that may be a problem in the real system. But this is, of course, this is reality. This is the reality, that this is the way it will look in the future. I mean, if you take India, you have different states, and it may be sunny, and you have limited transmission capability, and there may be outages in the lines, and so on. Okay, so now I have the final lecture, which is 1.5 hours, and I will take it in 10 minutes. Okay. Sorry. This I have as a general description of power system, but you also have it in other places. You have something first called regulation or control, you can call it, and then you have operation, you have in planning, and you have investments. Let's say an aeroplane, for example. You're sitting, you're a pilot, you're driving the aeroplane, and then the question is, it has to be stable. I have to land. I have to have fuel, I have to have speed, I have to go up, and I have to go down. Okay. Go down you will always do, but you should do it in a controlled way. That is the control. In the power system, you have primary control, secondary control, inertia, and these kind of things. Here, technology is extremely essential. You're never sitting up in the airplane and say that, oh, say, I should change the wings. No, it's too expensive, I don't do that. I mean, in the primary control, you don't say that, no, I skip the primary control, it's too expensive. No, no, here's the engineers. Here's very much engineers are sitting here. But it's still the same thing, keeping the balance. You have paper mill and you have offices, the same thing, anyhow. Then you have the operation. The question is, which is you often see, you come to the airport and there is a technical problem with the airplane. They must have research. Okay, it's not working, what do I do then? Should I wait for the next plane? No, that is filled also. So they must have some kind of reserve plans. I'm coming a bit later, so they must keep more schedules. Economical flying, so they should think about, and for example, very often the plane is a bit delayed, but then it's a bit faster, taking margins, how many margins, that they cannot schedule exactly. They are normally saying that we run on an economical way, but of course if the plane is late, when we run a bit faster. It's the same thing in the power plant sector here. Then you come into planning, air routes. Should we offer a new flight here from, should we only have one plane a day from Allahabad to Delhi, or should we have perhaps more? It depends on the market and so on. So this is, let's say, the planning. Power system, the question is when you should have maintenance and so on, and then the question is about investments. Should I have new aircraft or should I have new power plants? The important thing here, just in general, here we go from seconds to years. What is happening here, just in general, is that here it's very much technology. It's technology we are discussing here. It has to work. Here we have the engineers. On the other hand, if you come up to here, it's very much economy. Is this profitable to do this? But of course, remember, whatever you do here, all the other things must work. So if you want to buy a new aircraft, of course you have to think about how will I operate it, how will I plan it, and how will I run it. So I have a plane which is working. I have to keep margins. Perhaps I have to buy some extra planes. I have to have the routes, and they have to be coordinated so I can use the planes and so on. Or can I go and merge, as Air India is, for example, in the same, the Star Alliance as the Swedish company SAS. So they are coordinating. So formally I have my SAS card is working on Air India. And that is exactly in order to improve, make these kind of things easier. So you have to go from seconds to years. You go from technology to the economy. And here, security is absolutely most important issue. We will not have any outages. And I think outages is in reality more common than crashes here. So they are better than we know they are not. So that's the challenge that here, so here security is the important thing. Here the problem is uncertainty. We don't know what happen. Which prices do we have in the future? What is the demand? What is the cost and things? So economists, they love to work here. Here the economists, you very often have economists here. But I normally say that you should have, it's easier to move in that direction. It's easier if you know this. Because what I talked about rather much now, I have talked more in, you can call it this area here. That's what I talked about. In the beginning I talked about this, so much about dynamics. This is the issue. So I think it's easier if you understand this to go towards this. The problem I often have is that there are economists working in this area, and then I say that, sorry, but if you buy something, it has to work. You cannot only buy a thing because it's cheap. You still have to keep the control. Okay, so this was a very general issue about this issue. But the question is that when we have the markets today, that is the idea of what I will talk about, which I only have 2 minutes to do on 60 slides, I think. I can take up this. The question is, electricity then, because what is discussed today is that we should have a market, the question, and that is you should have competition in order to get the best solution for the future. And I will just say something about, very short about that. I think I take this one. Today we have something called vertically integrated. That is what you have in India here. You have more or less the same company that earns everything from the production sources down to the final consumers. So it's very much controlled. This means that you have a certain electricity price which is sent to the consumers, and that is in reality the cost plus the profit, and then minus a subsidy in reality. That's what I understand how the system works. In a deregulated market, it's exactly the same equation, but you move around it. In the deregulated market, the problem here is the following. Why should the company keep down the cost? That is one of the big problems in this vertical regulated market. For example, in Sweden earlier, it was like this, that you have a distribution company here. They are buying power here, they have a transformer here, and then they are sending power to the consumers. Here you have consumers, and they are sending power in that direction. And then the question is, how should they dimension this system? Should they have one transformer there, or should they have two, or should they have three transformers? From the reliability point of view, of course they should have three transformers. What is the incentive? Why should they have three transformers? The reason is that they have a so-called cost plus regulation, which means that profit is equal to cost times, let's say, 0.05. Okay, so they have some costs, and then they can earn 5% extra on that every year. The problem of that, with this kind of thing, which is very much cost-driven, which means that I buy three transformers, because then I have higher cost, I will earn more money. And the question is, why should I, for example, keep a higher reliability in my power plants? Why should I? Because the problem is that if I keep a high reliability, whatever cost I have, I buy a new power plant. That's nicer. So no one have the interest in that's the problem of the regulated market, and that is what we saw in Europe earlier. There's absolutely no interest to keep down the cost, because you will earn money anyway. These here, when you have a deregulated market, then you have some kind of electricity price, which is in some way set by the market. Then the profit you earn is the price you have on the market minus the cost. Here, you have the other issue, that the profit increases if you keep down your costs. So here you really get something that the companies start to think that, how should I, for example, let's say you take a coal power plant. I can put a lot of investments in the power plant in order to get it more efficient. I can try to make the maintenance so it works very often, so it's keep very good efficiency and so on. And if you keep a good efficiency, you will also reduce CO2 emissions and so on. So the benefit of having, let's say, a market and not a regulation, this is very complicated. How do you really make the companies being efficient here? So they care about making good units, because it must be the managing director on the top that really wants to have an efficient power portfolio. But it may happen that they earn more money if they have a bad plant and they buy a new plant instead. And then why should you? It's more costly. Here they have an interest to reduce the cost. But this doesn't say this is better than this one, because then you have the problem. This is exactly what happened in Sweden. We have a deregulation. They keep down the cost. Why should we invest in the grid? We have a grid. The best way is not to invest in the grid. Yeah, but you can get outages if you don't invest in the grid. Yeah, but that's not now. That's 10 years ahead. And we want to earn the money now. So that what the risk here is, that you to low reliability in the system instead. And today, for example, it is like this, that the big power companies in Sweden, there's a discussion. Yeah, but we may get outages in the future. We have to invest in power plants. No, why should we? Because they like to have a deficit of power plants, because as you showed you earlier, then the price go up. So they earn much more. So there's a risk with this, They don't. Here is the risk that you over-invest and you don't care about the cost. Here is the risk that you don't invest just because the companies that are profit maximizing, they want higher prices. Then I have 70 slides more, but that will be in the next course. Okay, thank you for today.